Good morning. The screen and I am audible. Screen is visible and I am audible, correct? Somebody please reply whether I am audible and the screen is visible. Okay. Okay. So I'll start. So today we will be discussing about the speed control, the basic speed control and the governing equation of electrical machine, mainly induction motor, asynchronous motor, in DQ reference frame for vector control or field oriented control. So first thing today I will be discussing, that is about V by F control. Okay. So why it is called V by F control? Let us understand that and how it is done. Okay. So we know already the RPM, that is equal to 120 F by P. So the pole I cannot change and 120 is a constant. So only the way to change the RPM is to change the frequency, change the power frequency. So if I able to do that, mathematically I will be able to control the speed. Okay. But in normally our power frequency is 50 hertz. So that voltage we can vary, but the frequency, it is normally straightforward, it is not possible. If I make a inverter, okay, if I make one inverter which is taking DC voltage and converting it to AC voltage, then by changing, and here if I use the PWM, we will learn it today slightly in this details. So if the frequency of the modulating signal of the PWM is changed, then the power frequency output of the inverter also will be changed. So in this way I can change the frequency, which will in turn change the RPM of the machine. But we know flux is another important parameter for the machine, which is nothing but the ratio of V by F, V and F. So now to control the RPM or to change the RPM, to increase the RPM, if I increase the frequency, then my flux will go down. To reduce the RPM, if I reduce the frequency, then my flux will increase. So, which is not advisable. So if my flux is reduced, then my machine will be underfluxed and it may not able to deliver the torque, rated torque. And to reduce the RPM, if I reduce the power frequency, then the flux will go up, machine will be overfluxed, which will cause the overheating of the coil, stator coils. It may in turn cause the failure of insulation system of the machine. So to do so, to maintain the flux level constant and also to change the RPM, the extent we will be changing the frequency, the same extent we need to change the voltage. So if I reduce the frequency by half, then I will reduce the voltage also by half, so that the flux is constant. Okay. So to do so, one power electronics arrangement is done. I am telling all the classical concept. So this is the controller, here is your motor. So this is a voltage controlled rectifier and this is a frequency controlled inverter. So I will make the control such a way that based on the requirement of my RPM, the extent I will change the frequency, in that same extent I will be able to control the amplitude of the power output also. So that's why this V by F, it is called variable voltage variable frequency drive, or sometime it is called 3VF, triple VF drive. Okay. Once the concept of PWM evolved, then by changing the modulation index of the modulating signal, I can able to control the amplitude, and by changing the frequency of the modulating signal, I can able to change the power frequency. This things is done by alone one inverter. Okay. So this is the very basic of open loop V by F control. For the closed loop, you should take the RPM and the current feedback, and you can use some PI regulator or PID, and based on that your modulation index and the modulating signal frequency can be altered accordingly. So this is the very basic fundamental concept of V by F control. Okay. Now we will be going about we will be just today we will be knowing the governing equations which will be required for vector control. As I was telling, vector control is very important control today for electrical machines, and we will be learning it in details, but as it is involved lot of mathematics, so I will go very slowly so that you can understand it. Okay, so these two equations are rotor voltage equation. So this is the, yesterday I told, this is stator direct axis equation, which is nothing but stator resistance into stator direct axis current plus rate of change of stator direct axis flux minus synchronous speed into stator quadrature axis flux. Similarly, stator quadrature axis voltage is equal to stator resistance into quadrature axis current plus rate of change of stator quadrature axis flux plus synchronous speed into stator direct axis flux. Okay, this is the flux equation of stator. Yesterday I told, here I have used LSS. So this LSS is self plus mutual. This is self plus mutual. So as here we know, the some portion of the flux, it will be influenced by the rotor current, so that is contributed by mutual inductance. So the stator direct axis flux is the total inductance into stator direct axis current plus mutual inductance into the rotor direct axis current. Similarly, for quadrature axis flux, that is equal to total inductance into stator quadrature axis current plus mutual inductance into the rotor quadrature axis current. Okay, so this is called stator flux equations. This is rotor voltage equation. Okay, it is very simple, similar way. So rotor direct axis voltage is equal to rotor resistance into rotor direct axis current plus rate of change of rotor direct axis flux. And as in the first lecture or second lecture I have told, the relative speed between the synchronous speed and the mechanical speed of the rotor is that will decide how many number of flux line will be cut by rotor conductor. So that's why here it is relative speed taken, that into rotor quadrature axis flux. Similarly, rotor quadrature axis voltage is equal to rotor resistance into rotor quadrature axis current into rate of change of rotor quadrature axis flux into plus relative speed into the rotor direct axis flux. So this is the rotor voltage equation. When we will be learning in detail about the, maybe tomorrow or day after tomorrow, we will be using this equation. So I will request you to take any book of mathematical modeling of electrical machines, and you can see in details with the equivalent circuit how this is made. It is very simple. It is very simple, as we know ABC to DQ and DQ to ABC transformation, we have already learnt it. So to conceptualize these things is nothing but to write the equation which will confirm the Kirchhoff's voltage law, nothing else. Now coming to the rotor flux. Simple, rotor flux also simple. So this LRR, that is equal to rotor self plus mutual. So rotor direct axis flux is equal to total rotor inductance into direct axis current plus mutual part into stator direct axis current. So this is induced from stator side. Similarly, rotor quadrature axis flux is nothing but total inductance into rotor quadrature axis current plus mutual into stator quadrature axis current. Okay, so we have learned stator voltage equation, stator flux equation, rotor voltage equation and rotor flux equations. Now I am coming to the torque equation. This already we have learned. We have established in details how from the rotational power, because torque is produced from the rotational power. So by taking the rotational voltage and multiplied with that corresponding currents, we will obtain the total rotational power, and from there if I divide, the power is basically the product of torque into RPM or angular speed. If you divide by the angular speed, you will get this equation. So this is the torque equation, instantaneous torque equation. Okay, this is the instantaneous torque equation. So these sets of equations will be used to implement the vector control. Already we discussed, I given you the glimpse of vector control, that it is nothing but vector control is nothing but to convert the torque equation, that means this equation of induction machine, which is be analogous to separately excited DC machine, which is nothing but some constant into some flux into the armature current. So to do so, I have to vanish this. To vanish this, using some control technique, I have to make this flux 0. If I make 0, this part will be cancelled and this entire part will be treated as constant, and this psi RD is the field flux and the stator quadrature axis current is nothing but the armature current. So we will be learning slowly how to, by adopting some control technique, how to make that psi RQ 0. If you make the psi RQ 0, then what are the, so whatever the equations we have learned so far, this total there will be 8 equations, 8 and 1, 9 equations. From that 9 equations, if I put this psi RQ 0, how the governing equation will be changed, and with that changed governing equations, the same thing will be implemented in power electronics and control. Then our vector control will be achieved. Okay, so what we are going to do in that governing 8 governing equations, we will be substituting the value of psi RQ as 0. Then it will be coming as a different form. With those equations I will implement physically in the microcontroller and the power electronics. Then our job is finished. Okay, so today only I told further calculation we will be doing tomorrow. So today only I have shown this 9 equations, and I would like to request all of you to memorize these equations and also take some standard book of mathematical modeling of electrical machine and review once again. I know you all of you know it, but still you read once again. So today we will be doing one small simulation. So in V by F control, I was telling you, you need to have the rectifier. Means input is AC, so here I have given 415 volt 50 hertz, and this is the silicon bridge, and this inductance and capacitance are used as filter. This is a 3-phase 2-level inverter, you know all. So these two switches for each phase has two leg. Each leg have two switches, one upper and lower. Both are complementary switches. That means if the both switches are on together, then it will create the short. The DC will be directly shorted through that path, and very high current will flow, which will damage the junction of the semiconductor device. So that's why whatever pulse I am giving in the top switch, you see I have this NOT gate, I have inverted it and given in the bottom switch. This is my modulating signal, and the amplitude of the modulating signal indicates the modulation index, and the frequency of the modulating signal, it is denoted, it will predict the speed of the machine. Okay, so this is the induction machine. It's a 6-pole machine, and here I have loaded the machine with some torque of 64 Newton meter. Now let us simulate it. As I told, V by F is a scalar control, and it's an open loop control. We don't have any control over the current, so this will take inrush current. You see, this is the speed curve, and after accelerating, you see the speed is 981. So it is 6-pole machine, so synchronous speed is 1000. So it is deviating 982, 18 rpm from its synchronous speed. So that is the slip, and that's why it is producing the torque. So in asynchronous machine, definitely it will produce torque when it will be deviating, it will be slightly away from its synchronous speed. When it is going to, if you remember the speed torque characteristics, if the speed is exactly with synchronous speed, then the torque is 0. That means if slip is 0, then torque also 0. Okay, and we learn the torque equation, instantaneous torque equation. So there, if you put slip 0, then your torque also it will become 0. Now if we see the current, you see, till the machine is getting accelerated, that means till this position, the machine is behaving as a short, as I was telling. So it is drawing that high inrush current, and once it is completely accelerated, then it is taking the rated current. Okay, so now say I want to operate the machine in lower frequency. Simply you change the RPM, and you change this modulation index also, otherwise my machine will be underfluxed. Sorry, machine will be overfluxed. You see now that RPM is come down to 500 because my frequency is half. Okay, so this is the simple technique to implement that you can do for as a small project. To see, you can take a three-phase silicon bridge, or you can do it first for small motor. You can take some small 370 watt induction motor, and you can use some standard DC source in your app lab DC power module. Then you can take one inverter bridge. This lot of standard companies are available in the market, so you can take it. You can take one microcontroller, generate the PWM, give the pulses with date time. That means practically what will happen in practical case, say this is my positive side pulse, and if give my negative side pulse, even though it is complemented, but the thing is, at once the high pulse is coming in the high leg, and the same time if the low pulse is coming to the bottom leg, a bottom switch, what will happen? Immediately the switch cannot off. It will take some time. It will take some time like this. So still you see this period switch is just switching off. So I have to consider this time. This time this pulse should not go high. After that only, after this completely that switch off, it will be the pulse should not raise from this position. Once the switch is completely off, then only this pulse go high. So this time is called dead time. So we'll learn later how to generate this dead time. So as PWM is required to generate to control the inverter, so we will learn today the basics of PWM. So this syntax of the code already I explained several times in general syntax how it is. This is the main function. This is the main function, and this while one loop means it is always true, and this is the place for initialization. The controller means it will execute for once. Return 0 means that as it is not returning anything, so I have written 0. So here first I have used the pin config, like pin config one function. So this will define the nature of the pin. You see that pin config function I have elaborated here, and here I have used one register called DDRB. DDR means data direction register. Data direction means whether the data will go from the from the microcontroller to outside or from outside to microcontroller. That means whether the pin is input or output. So if I want to make any pin as output, then that particular bit is to be set 1. Other case it should be 0. So here I have used 2 PWM signal. So that's why you see in port B 1 and 2 I have set as 1. So that means PB1 and PB2 will be used as output. So if you see that my circuit, if I see the circuit, you see this is PB2 and PB1, that is as output, it is treated as output, so that's why I made those bit as high. Now this PWM will be generated using the timer. Timer can operate different mode, so we need to configure the timer in PWM mode, and for that I have used this function. We'll be knowing it. This is the status register. Here we'll be using the interrupt. Interrupt means we'll be using the overflow interrupt. So as I told, if you want to use any interrupt, first the microcontroller should enable globally. The global interrupt should be enabled, which is the ith bit or 7th bit of the status register. So that's why I made it. This TCNT1 I have using timer 1. So this is the timer 1 data register which I initialized. Now we will be knowing what are the bit setting we have used for these 3 registers. So first is TCCR1A. So let us find out. Sorry, TCCR1A. This is the TCCR1A. Okay, so we will be using this 4-bit and this 2-bit. So we are going for PWM mode. So let us see. This is the phase correct PWM. I will tell you all these things. So you see here, if I set this 2-bit 1 1, that means set output compare register while up counting and clear while down counting. What is that? So as we know, timer is repeatedly counting the time. Means from here it is going counting, then it is coming, going, coming, like that continuously the timer is doing this job. Now if I set a value, say I set a value of this output compare match like this, then what output we will get? If we set 1 1 in that 2-bit, then while the compare match occur, then the pulse will set and remain it at high state, and while down counting, this is the up counting, and while down counting, when it is match, it will be clear. So you will get a PWM like this. Okay, here say it is like this, so you will get a pulse like this. This is the duty cycle increased. So that's why the first 2 MSB I have used 1 1. So that means the output will be high while up counting, means the compare matches while up counting, this will be set, and clear while it will be down counting. And the next 2-bit I have used 1 0. So let us see what is that 1 0. That 1 0 means clear while up counting and set while down counting. It is opposite to that. It is opposite to that. That means if I take another thing here, so that means if the pulse is high, so once the compare match occurred, it will clear and hold it, and while down counting, whether again it is match, it is going to high. So you see, just we are getting the inverted pulse. So as I told, for the complementary switches, so this is the up counting. So while up counting it is matches, so immediately the output drop to 0, and from down counting, when it is matches, the particular pin set to high, which is just opposite to earlier 1-1 setting. So as in the inverter, we need the pulse and its complementary pulse. So by changing these 4 bits, we can control it. Which one will be positive, means a top switch pulse, and which will be complementary switch pulse. Okay. So now we have understood the inference of this 4 bit. Then coming to this last 2 LSB, because here you see this is the waveform generation register. So these other 2 bits will be in the TCCR1B. So there is a table of, you see, this is the waveform generation register. So we have used 10 bit. So these are all, if you read that, I am not going in details of all these things because it will take time if I explain line by line. So we are using 10 bit phase correct, 10 bit phase correct PWM. So you can read what is phase correct PWM, what is fast PWM. So that's why, that means these two, this WM10 and WM11, it is to be set 1 and 1. So if you see the code, that 2 bit I set 1 1. Okay, and other bits are, as I told, this will be other bits are there in TCCR1B. So you have to check that one. So now I am going to TCCR1B. You see, in TCCR1B, I am not using these 2 bits. I am not going to tell the function of these 2 bits. Okay. So you see that from the WGM waveform generation table, this, what for 10 bit phase correct, we need to set it as 0011. So these 2 bits will be 00. So here you see in the code, these 2 bits are 00. Now here you see the last 3 bits I have used 001. Sorry, here 001. What is that? So if you see the last 3 bit, this is the prescaler bit for the clock. So this will define the switching, that PWM frequency, the switching frequency. So in that data sheet, if you read the PWM portion, how to calculate it, their clear formula is there. From there you can find out what should be the PWM frequency. You can read it. If you not able to understand, you can ask me the subsequent, anyway, in the when we will be generating the sine PWM, that time I will be explaining you all these things, how to calculate, how to set the PWM frequency and all. So here we have used 001. That means the clock is divided by 1, no prescaler, exact clock will be used. And you see, if you set these settings corresponding, you can maximum for low frequency, you can divide the clock by 1024. For that you need to set that CS bit as 101. Okay. So we have understood up to this. Now I am going to, here on register I have used, that is timer TIMSK, timer interrupt mask register, and the LSB I have set as 1. Why so? We'll read it. So TIMSK 1. You see, sometime you see, this is TIMSK 1. Some people, some previous lecture asked, sir, whether using Arduino or something we can control the motor or not. Yes, you can very well can do, but you should not use the library function of that IDE. It is my observation and my experience. If you use the library function, then you will be losing the control over it. Is a standard purpose it is made, so you should not use that. You can use the IDE. If you are familiar with a particular IDE, you can use that. Subsequent, after this course, there will be basics of microcontroller. I'll be teaching this 8-bit controller in details. Then you'll be going for 16-bit. Like that, you can also join in that course, so that you can thoroughly you will understand the thing. And as I told already, if you understand any microcontroller, it may be 8-bit, 16-bit or 32-bit, whatever may be, then you can, if you take the help of the data sheet and if you know the digital electronics slightly, any controller you can program it, write the code. So frankly speaking, this vector control was done first in I have done it in this 8-bit controller. One of my student of SRM University, he did it. I'll try to get the circuit, the PCB. He made the complete PCB, and the same during his campus interview he explained that one only, and he got job in, I think, Merchant Navy or somewhere. He is controlling the inverter, power electronics part of that ship vessel. So you have to learn the thing thoroughly, any one of the things. It will be easier to present your knowledge, and you can perform better. It's in my opinion. So here in TIMSK 1, we have used that LSB TOIE. So let us see what is that. This is timer overflow interrupt enable. When this bit is set to 1 and the I flag of the status register is set, then the timer or counter overflow interrupt is enabled. That means once the complete counting is over, one interrupt will be generated. We know what is interrupt. Already I explained yesterday what is called interrupt. So now if you see the code, I have enabled now overflow interrupt, and in that interrupt service routine I have written that this is the vector for timer 1 overflow interrupt, and in that this OCR1A and OCR1B, that is the output compare register, there I am giving the value. So this is set for 10-bit. So 512 means it will produce half of 1024. 10-bit means 1024, half of that means 512. So it will give a PWM of 50% duty cycle, and this will give the inverted PWM of 50% duty cycle. So let us see how it's work. Let us see the waveform. You see, the yellow color is the PWM 50%, it's the PWM of 50% duty cycle, and the blue color is the inverted of that. So now let us change the duty cycle. Now let us change the duty cycle. So let us make it is 25%. generate the hex file. So hex file is generated. And you see that yellow color one, it is giving the duty cycle is increased. So in this way you can generate the PWM. This is the fundamental basics of PWM for any microcontroller. Okay. So as this inverter, to control the motor you need inverter, and inverter will be controlled by PWM. So that's why I given the glimpse of PWM, how it is to be generated. In some subsequent lecture we will be learning how to generate the sine PWM for motor controller. Okay, so this was all about today's class. Now if you have any question you can ask me, or I can terminate the session. Any question is there? Would you like to ask any question? Okay, then thank you so much. We will see you tomorrow. Till that, stay safe, because this pandemic is increasing. It is an increasing trend all over the country. So stay safe, be at home. Output of the inverter follows the how modulation index is controlled. Yeah, modulation index is controlled by the I'll tell you when I will be generating the sine PWM. I will be telling you practically how it is to be controlled. Output of the inverter follows the PWM period. No, PWM period is the it will define the switching frequency of the IGBT. The PWM period will define the switching frequency of the semiconductor device. So definitely your PWM frequency should not be higher than the switching frequency of the IGBT or MOSFET. Okay, so I am terminating the session.